Okay, this video is to maybe help you who are struggling with the exercises involving interpret change and exponential models with manipulation. These sort of exercises require you to take a given equation and rewrite it in a different way, but in an equivalent way, using kind of the exponent rules that we already know. I'm going to go through a couple examples with you that should be similar to some of the ones in the practice, and hopefully that will help you in doing a little bit better on these exercises than what we've kind of been seeing so far. Also, after you watch this video, if you're still stuck, don't be afraid to pop on to class today at 1. Okay, first example. How long does it take the population to decrease to 1/4 of its original size given the model b of t equals 2,000 times 9/16 raised to the t power, where t is in months? So, based on this model, this equation, our starting population is 2,000. The decay factor is 9/16, and since t is in months, basically it's saying it takes 1 month for this population to decrease by 7/16 of its starting amount. And the reason I know it's decreasing by 7/16 of its original amount is because my decay factor is 9/16. If I take 2,000 times 9/16 to the first power, I will get an answer that's smaller than 2,000, and it will be exactly 7/16 smaller than 2,000. Because when you multiply by 9/16, something is losing 7/16 of its value. I think that should be clear with all the b-value discussion that we've had, but if not, you might want to go back and watch that video again or ask questions in class. So anyway, again, this model shows a decrease by 7/16 of the original size, and we want to know how long does it take the population to decrease to 1/4 of its original size. Well, if something is decreasing by 1/4 of its original size, the decay factor would have to be 3/4. So what I need to do is I need to rewrite this equation with a decay factor of 3/4. So I have 2,000 times 9/16 to the t. But I want to write an equivalent equation where my decay factor is actually 3/4 instead of 9/16, because the question asked, again, how long does it take for it to decrease 1/4 of its original amount? So, how does 3/4 relate to 9/16? Well, 3/4 times itself, so 3/4 times 3/4 is 9/16. So 3/4 squared is the same thing as 9/16. So what I'm going to do is I'm going to write 3/4 squared to the t power. Because again, 3/4 squared is the same thing as 9/16. So now I have a power raised to a power. So this power here and this power here, a power to a power means I multiply. So my equation can be rewritten again, 2,000 times 3/4 raised to the 2t power. So now I've rewritten my equation that has a decay factor of 3/4 instead of 9/16, which is what I wanted to do. So the question says, how long does it take for this population to decrease to 1/4 of its original value? Well, right now it shows it's decreasing by 1/4, but the exponent now instead of t is 2t. Remember, our exponent was in months, so I know that 2t has to be equal to 1 month. So then when I solve for t itself, I divide both sides by 2, and I get t equals half a month. So that tells me it takes half of a month for this population to decrease to 1/4 of what it originally was. So the answer to this question, how long does it take the population to decrease to 1/4 of the decrease by 1/4 of the original size, that answer would be half of a month. So that should help you with some examples that are similar to that on the exercises. Okay? Another problem that shows up for you is something that looks like this. Here's the model. P of t equals 1.03 raised to the 4t plus 5 power. It says, given the model above where t is in weeks, how much is the population increasing each week? Well, clearly the model does not show you how much the population is increasing in weeks because the exponent is not just a t, it's 4t plus 5. So we want to somehow rewrite this equation so the exponent is just a t. So we got to use our exponent rules again to kind of help us out. So I got 1.03 raised to the 4t plus 5 power. Because there's addition going on, I can separate this into a multiplication. We know that when we multiply, we add exponents. So I know that I could have a multiplication going on of 1.03 to the 5th times 1.03 to the 4t. Okay. (1.03 to the 4t). The reason this statement over here is equivalent to the original because when I multiply, I add exponents. And if I would add the 5 and the 4t together, it would equal what I started with, 4t plus 5. So I'm going to leave the 1.03 to the 5th power alone and just leave it as is. But on the other one, the 1.03 to the 4t, I'm going to write that as a power raised to a power because I have multiplication. So I have 1.03 to the 4th, but then all of that raised to the t power. Because again, when I take a power to a power, you multiply. So this is equivalent to the previous step. And now I can finally, again, I'm not going to mess with that, but I am going to go ahead and figure out what 1.03 to the 4th power is. I'm going to get out a calculator to do that. Just one moment. So 1.03 raised to the 4th power is about 1.1255. 1.1255, and that now is raised to the t power. So you'll notice I've changed the equation from what I had up here originally to now this. This looks a little bit closer to, our y equals a times b raised to the x power. All right. I don't really care what a is in this case because, again, I want to know, given the model where t is in weeks, how much is the population increasing each week? So I'm really just looking at this value right here. I'm looking at the growth factor. If 1.1255 is my growth factor, how much is the population increasing each week, assuming t is in weeks? All right, well, if the growth factor was 1.1255, that means I must be experiencing a 12.55% growth each week. So that would be my answer to the question that was originally asked. Given the model above, how much is the population increasing each week? So I had to do a lot of algebraic manipulation to get my equation to just have that exponent right here of t. And once I had that, I just had to look at this b value, or the value that is being raised to the t power, and then I could answer my question. There's a 12.55% growth each week. Hopefully this helps you with this set of exercises.